The purpose of this demonstration mini lecture is to review the basics of three periodic trends: atomic radii, electronegativity, and ionization energy. They are tied together. They are one of the reasons, or how we can really explain the periodicity, the repeating behavior of elements that occur on the periodic table as we use the function of their atomic number. In any case, let's start with the most important of all, and that is atomic radii. As you see on the board here, atomic radii, as I'll point here, is the driving force of all the periodic trends. If you can understand how atomic radii changes on a periodic table and why it does, and the implications of those things, you know how ionization energy, electronegativity, and then bonding can all occur, and the types of bonds that occur on the periodic table. In any case, let's get started with atomic radii. Now, if you look across the periodic table, you'll notice that lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine represent almost all the elements of group 2. I am missing neon, and I'll just write it in here. And for fun's sake, we'll put neon here. And if you notice, I've got these positive charges for each of these. And these positive charges are the nuclear charge. This is the number of protons. Lithium is atomic number 3, so it's got a positive 3 charge for lithium. Beryllium is positive 4. Boron, don't be 1. Then we got carbon, nitrogen, oxygen, fluorine. And of course, atomic number 8 for neon would be, neon would be plus 10 because its atomic number is 10. So what I'm writing is the charge due to the nucleus, and that nucleus, of course, the charge is due to the proton number. Now, if you notice, I have these circles, or the atomic radii in red, circling these elements on the second row. And you notice they're getting smaller, and they're getting smaller primarily because we're adding more protons. Protons in the nucleus are attracting the electrons that are outside the nucleus in an empty space that Ernest Rutherford discovered in that gold foil experiment. And what's happening as the nucleus gets stronger, it pulls in these electrons in closer. Now, electrons and protons have fundamentally the same charge, +1 and -1. They have the same size, but differences in charges. Yet it's the electrons who move because electrons are about 1,836 times lighter. So you tie them together, they both have the same force of attraction, but the lighter one's going to move. So obviously, as we increase the number of protons, we pull in the electrons. And since the atomic radii, or atomic radius, is from the nucleus to the outermost electron, you can see that these radii get smaller as we go across. And it makes sense. Anytime we go across a period or a row on a periodic table, or an energy level, right? Second energy level, n equals 2 here for the second row, the radius has to get smaller. And we get smaller by, the smallest, of course, is the noble gas in that row. And smallest because it's got the greatest number of protons for that energy level, okay? At least early on. Now, so you should know that an increase of nuclear charge, or protons, makes the atom smaller as you go across. Now, using that same understanding, you may probably think that, well, as I go down a group, now I have sodium and potassium here, I should get smaller. Since sodium is +11, and this is +3, this should get smaller. But, in fact, what happens, or we find, is that this radius is actually much bigger. How can it get bigger if it's got more protons? Very simple. Okay, it's a different understanding. Here we're filling electrons in the same energy level. 1s, 2s1, 2s2, 2p1. We're filling the second energy level. So if you look with me here, lithium has 3 protons in its nucleus. The first energy level is, there's 2 electrons. And in the third energy level, this would be the the first energy level, 1s2, has 2 electrons. And the second energy level only has 1 for lithium. So when we look at the atomic radius, we're looking from this point to this electron. Great. Now we go to sodium. Sodium is +11, and you may think, wow, that's going to pull in all electrons. But it's from the nucleus to the outermost electron when you're dealing with atomic radii. That must mean that this positive charge has to somehow get through not only the 2 electrons the lithium had to, but it also has to get through another entire energy full of electrons. So these protons somewhat get shielded by these extra layer of filled energy levels, and it makes it tough for this electron to feel this nucleus, so it's able to go a little farther away. Another way to explain it is if you're adding an extra shell of electrons, and I'm using that kind of loosely because they're not shells, okay, they're standing waves, but as we add electron energy levels, the distance by which those electrons exist from the nucleus do increase. As you learn something in quantum numbers, as you know, n equals 2, n equals 3, that indexes the size of the orbitals, those standing waves. So electrons that fill outer orbitals, if you're going to the third energy level, have to be farther away anyway. So you have a proximity issue. I'm farther away than this one electron is. So therefore I feel the nucleus less. And two, because there's more electrons in between that positive, you are shielding that positive force and making it harder for the electron to feel the nucleus. So we say the effective nuclear charge, okay, could be somewhat lowered in this case. Okay? And that's one way to think about it. You call this the shielding effect, you'll have people discuss, or the idea that you're just adding an extra layer of electrons. And that's the reason why we get bigger as we go down, because we're adding more electrons, making it harder for the nucleus to feel that outermost electron, or an extra layer of energy shells that are adding always farther away. So the atom has to get bigger. Now, if electrons are existing farther away as you're going down, they're being loosely held if they're bigger atoms. And if they're being held closer, they're being held tightly. And to really, really understand that, I have Elvira, the outermost electron here. And so you understand this very carefully, I've got her in a sash. Okay, a sash is like if you were in a pageant. We're going around the net, around the shoulder, and under the arm here. And what I'm going to show you, I want you to visualize. I'm the nucleus, and Elvira, the outermost electron, my friends in chemistry here, is that farthest away. So a big atom has electrons that go farther away. And as you can see, it's hard to control that outermost electron. And sometimes I can lose it very easily because I don't control electrons very well if they're farther away from me. Yes, big atoms, okay, will lose electrons easily for two reasons. Number one, they have a low attraction for electrons in general because electrons can exist farther away. So they're able to lose them because their attraction. We've got a fancy word for attraction, pinky up when you're talking fancy. It's called electronegativity. Electrons that exist farther away don't have much attraction for their outermost electrons. They can't. If they did, they wouldn't be so farther away. They'd be pulled in. So it's very logical. Atoms that are smaller, that have the electrons held tighter to them. So this would be like a fluorine. I go in a circle now. We'll see how close I keep Elvira to me, that outermost electron. And you would say I have a high attraction for electron. Well, why? That high attraction is called electronegativity. It's high because I'm able to pull in and attract those electrons tighter. Now, the third and final one is electronegativity. Ionization energy. Sometimes you'll hear it as first ionization energy. Well, first ionization energy, or ionization energy, is the energy it takes to pull an outermost electron away. Well, these guys here, my friends, I have one electron, and they hold on to them loosely. It won't take much energy to pull the electron away. In fact, because they lose electrons so easily, all right, as we keep saying, they tend to become positive ions. And they have a low energies needed to pull one away, so they do so very easily. And they have low attraction for electrons. They don't tend to gain them, they tend to lose them. These guys have a high attraction called electronegativity, and because they have a high attraction, not only do they attract their own, they fantasize and creep for more to gain. These guys love to gain electrons, and that's your yin and yang in chemistry. The ability to lose, okay, and ability to gain, because essentially the difference in the size of the atomic radii. So as we go through this, with those crazy visuals, atomic radii, as you go across, decreases. The electronegativity, we'll just do En. Electronegativity has to increase. That's the attraction. And IE, ionization energy, also increases. Why would it increase as you get smaller? Ionization is the energy it takes to pull electron away. So if I'm holding on to my outermost electron really tight, won't it take a lot of energy to pull this away from me? Absolutely. It's logical, people. Here, as we get bigger in the okay, as we go down, atomic radii increases. Okay, electronegativity has to decrease, and of course, your IE, ionization energy, has to decrease. Why does it decrease? As I get bigger, as I go across and down, I get bigger, I hold on to electrons more looser, I tend to lose them. It means I don't have attraction, it doesn't take much energy to release them. As I get smaller, I attract them more, and it takes a lot more energy to pull them away. Hopefully you can see how these three, okay, trends are tied. And by looking at the periodic table and understanding atomic radii, you can predict those three basic trends. And you can look and see who's more reactive. Okay? This, we say, is a non-metal area. They're smaller. They have a smaller radius, higher attraction for electrons. It takes a lot more energy to pull them away. They gain electrons. These guys are bigger, lower attraction, lower energy to take away. They tend to lose. So when you put a sodium next to a fluorine, the fluorine will take his lunch, take his electron. This guy becomes negative, this guy becomes positive, and we have something called an ionic bond. And that's really the first basis of bonding. Looking at the periodic table should give you an idea of what things can bond, what things cannot bond. Now, if you look at your nonmetals or your smaller elements, and what defines a nonmetal is these small radius, high ionization, high electronegativity. These guys can bond with themselves to become stable, and they do so because they have to share, because they're both strong for electrons. But understanding these trends opens the door for understanding of chemical bonding. And looking at the periodic table, you can see the yin and yang. The ability to lose, that's metals. Ability to gain, non-metals. Hope that helped.